off, sir is not there. Ah, sir is come.
Sorry, my computer
Hello.
got shut down. Okay. Hello.
The mic is off.
Hello.
Yes, sir.
Okay. So my computer got shut down. That's fine. We'll continue. So one more place where we use the steel casting is where the shape is complex. Like you take the bulbous bow region or the aft end of the ship. So the shape will be very complex like this. Okay, there you cannot go for a normal plating. If you're going for a normal plating, you have to take that plating for a bending machine. If you're bending the plate too much, then there will be a lot of internal stresses developed. So to avoid that, we go for casting. Okay, so that is the place you go for casting. Then what is the difference between casting and forging? What is difference between casting and forging?
So
And
casting the metal is molted also, but
molded and it is
in
poured into a
forging you
mold.
will
Mold and it is
uh,
cooled. What about
molted,
forging?
and in
Forging we are doing
the
hot
forging
work.
we used hammer to make it in a shape.
Yeah, okay. So forging, we're going to eat the metal, same we're going to eat the metal and we are going to bring it to a semi-solid state, okay. We are going to bring it to a molten state where you can work on it. Then they're going to exert external pressure, they're going to exert some external forces on the molten metal and they're going to bring it to whatever shape they want. Okay, they're going to they're going to use some like pressing machines or something and they're going to bring to whatever shape they want. That is in forging. Okay, so casting is widely used in ships. They're used in for fabrication of stern frames, for fabrication of stem bar, for fabrication of rudder post and this bollard bits and everything. Okay. And in some places in the ship you need the material should be very hard. For example, you take a bulk carrier, you take a bulk carrier, this is a bulk carrier and this is hatch opening. Okay, this is hatch opening. The grab crane is going to come down in this and say the cargo is here, this is a cargo. The grab crane is going to come, this is a grab crane. Okay, the grab crane is going to come and it is going to rub on the surface. This plate is your inner bottom plate, inner bottom plating of the ship. This grab crane is going to come and take the cargo from here. So what happens, this grab crane, it is a metal, it is made up of metal steel. So it is going to come and rub on the inner bottom plating. So what happens, like one times two times it is enough, but if it is doing for like 100 times 200 times, the material thickness will be keep on decreasing due to abrasion between the grab crane and the inner bottom. The material thickness of inner bottom will be keep on reducing, and after some time a dent may form in this, dent or holes may form in this. To avoid that, what we need to do is we need to use a steel with good hardness, a steel with good hardness. So what we do is we go for carbon manganese steel. Particularly for bulk carrier in the bottom, we go for carbon manganese steel. Carbon manganese steel, what is the disadvantage? It is very prone to corrosion and the toughness is very less, but the hardness is very good, the strength is very good. We are increasing the carbon content and we are using in these places. So wherever you need hardness, we have to increase the carbon manganese steel, but the carbon content is more. Okay, understood? So that is one application. So you have to think which part of the ship is going to undergo which kind of stresses. So based on the stress, if it is a tensile stress or compressive stress, you have to go for high tensile steel. If it is going to undergo abrasion, you have to go for ardent steel. Ardent steel means with more carbon content. Clear? Then now there is one more topic. We'll go into the testing of steels. Okay, before that, I'll give some more examples of the steels where the materials are used. Then if we take the stainless steels, see, stainless steels are very costly because the chromium content in the stainless steel is around starts from 15% to 30%. Okay, the chromium content is very high, and the price of chromium is very high compared to steel and other metals. So the price of stainless steel is more. So what we are going to do is we are not going to use in a big structure like ship. Even though it is having good property against corrosion, we cannot use in the ships because the price is very high. So what we are going to do is we are going to take a normal mild steel plate. We are going to take a normal mild steel plate. On top of that, we are going to coat with stainless steel. This is stainless steel coating. This is stainless steel coating, and this one is mild steel. So you'll find this kind of plates in the ships, that too in specific places where corrosion is very dangerous. Like you take a ship, a tanker ship, which is carrying a cargo which is corrosive in nature, which is more corrosive in nature. For ships carrying cargo which is more corrosive in nature, you have to use tank material should be coated with the tank plating should be coated with stainless steel. Okay, suppose you take crude oil, you take example of crude oil in oil tanker, the inside walls of the tank, the inside walls of the cargo tank will be coated with stainless steel. The inside walls of the cargo tank will be coated with stainless steel. Okay, the inside walls of the cargo tank will be coated with stainless steel. So this is one application. Then one more topic we have in this chapter: testing of materials. See, when the steel comes from the steel plant to the shipyard, there may be a surveyor coming from the classification society, and he will be testing the material. He will be testing the material to check whether the mechanical properties are according to the classification society requirements. Okay, so a surveyor from the classification society will visit a shipyard for checking whether the mechanical properties are according to the classification society rules. Okay, then only you will give approval, then only you can use that material in the ships. So what are the normal properties he is going to check? What are the normal properties he is going to check, and which properties are more important? He is going to check the strength first. Okay, he is going to check the strength. Properties of steel. He is going to check the strength. Strength means there is two parameters: yield stress, the maximum yield stress, the yield stress value, and ultimate tensile stress. Ultimate tensile stress. Ultimate tensile stress. You're going to check this. What is stress actually? What is stress actually? Stress is ability of material. Stress is ability of material to withstand a force. To withstand a force. Ability of material to withstand a force. What is formula for stress? What is formula for stress? force by area. Force by area you can write as Newton per meter square. Force by area. This is formula for stress. Okay. Now, by looking at the value of field stress and ultimate tensile stress, we can understand what kind of forces this material can withstand. How much force this material can withstand. Fine. The next important property is toughness. Okay. Or before that, we will go into ductility. Next important ductility. If the metal is having good ductility, then what you can do is you can convert that metal into any shape. You can convert that metal into any shape. You can change the form of the metal that easily. It is easy to bend. It is easy to elongate. It is easy to compress the metal. So all this is possible only if it is ductile. Opposite of ductility is what? What is opposite of ductility? Ductile. What is opposite of ductile? Brittle. Opposite of ductile is brittle. So when a force is given on a brittle material, what happens? The material will crack. The structure will crack and it will break. What about ductile structure? Ductile structure will deform. Ductility means what? Ability to deform. Ability to deform. Deform in the sense it can elongate. Elongate means increase in size. It can elongate. It can compress. It can get compressed. Okay. It can change in size. So all change in shape. So all this is possible if the metal is having ductility. So ductility is a very important factor. Understood? Ductility is very important factor. If ductility is very less for a steel, if ductility is very less, what happens? Ductility is very less. Then what happens? If you are applying a force, it is not going to deform. It is going to immediately fail. Deform in the sense, see, suppose a rubber band is there. You are pulling a rubber band. What happens? It will be deforming. It will be increasing in size, and after some point of time, it will break. There is some time, no, there is some limit in which it is like elongating. After that only it is breaking. But what about brittle material? When you give a force, immediately it will break. So that is brittle material. Fine. The second point is ductility, ability to deform. Then third point is notch toughness. Third point is notch toughness. See, toughness is in between what you can tell the brittleness and the softness. If you are giving a force on a brittle material like a stone, you go and hit a stone with an hammer. What happens? Cracks will develop immediately. You go and hit a material which is very soft. You go and hit with aluminum or something with a hammer. What happens? It is like very soft and the cracks will not develop. Toughness is in between this. Toughness is in between the brittleness and the softness. Okay. If the material is having good toughness, if the material is having good notch toughness, then cracks will not develop. If the material is having good notch toughness, cracks will not develop. Cracks will not develop. So the notch toughness is very important for fatigue deformation and for the fracture deformation. Cracks will not develop if the notch toughness is good. Understood? So which steel is having good notch toughness? Carbon manganese steel or high tensile steel? Which steel is having good notch toughness? When the notch toughness will decrease, if the carbon content is increasing, notch toughness will decrease. We have seen this yesterday, right? If the carbon content is increasing, notch toughness will decrease. In high tensile steel, what we are doing? We are not increasing the carbon content. We are increasing the content of micro alloying elements. Like we are increasing the content of aluminum. We are increasing the content of titanium, vanadium, niobium, so that there is no need for increasing the carbon content. So when you are decreasing the carbon content, the notch toughness will increase. What is meaning of notch toughness? Cracks will not develop. Okay. cracks will not develop. You can tell like the ability of material to absorb energy. Ability of material to absorb energy. Okay, the ability of material to absorb energy. Understood? Have you noted on this? Okay.
Yes, sir.
One more point is hardness. Can someone tell me? Can someone give some examples? Which part of the ship hardness is very important? For which part of the ship notch toughness is important? For which part of the ship hardness is important? For which part of the ship strength is important? Can someone tell me? Try. What about the inner bottom of bulk carrier? What about the inner bottom of bulk carrier? Strength is important or hardness is important? I told you the inner bottom of bulk carrier. Inner bottom of bulk carrier, the grab crane is going to come and rub. Crane is going to come and rub like this. Like an you have seen JCB, right? JCB that bookline. They'll come and rub the mud, no, like that. The grab is going to come and rub the inner bottom of steel. So what will happen here? Abrasion will take place. So which is important for inner bottom plating? It is not strength. It is hardness. It is hardness. Okay. Then what about the midship region? Midship region, the deck plating, the bottom plating. What is very important in the midship region? Strength is
Toughness,
important.
sir.
Why? Strength is important.
Toughness.
Why? Because of fogging and sagging deformation. Because of fogging and sagging deformation, huge bending stress is acting in these places: midship region, deck, and the bottom. So what is important for them? For them, the strength is important. You have to choose a material with good yield strength and tensile strength. You have to choose a material with good yield strength and tensile strength. Understood? And ductility is also very important because they have to expand. They have to expand. They should not fail immediately. They should be expanding, elongating. Okay. And what about notch toughness? Which part of the ship the notch toughness is very important? Always try to remember the fracture, the failure is going to take place in the weld region. Suppose there are two plates, you are welding two plates, okay. So the weld region only the fracture is going to take place. So the notch toughness is important for the weld area, that too in places of high stress concentration. The notch toughness is an important parameter where in high stress concentration places. High stress concentration, I will discuss this later. High stress concentration places, that too mainly in the weld region. Okay, in these places the notch toughness is the important parameter. Okay, in these places the notch toughness is important parameter. Understood? Can I wrap this?
Yes, sir.
Then what is hardness? Hardness is ability of material. Hardness is ability of material to resist abrasion. Okay. Hardness is ability of material to resist abrasion. Clear? Then we are going to the topic of material testing. I'll present you one video. You watch that video. Try to understand what is tensile testing. Okay. Tensile test we are doing for calculating the yield stress value and for calculating the ultimate
Conducting
stress value.
tensile test, 500 diameter tensile specimen.
Can you hear the audio of the video? Can you hear the audio?
Stainless steel material.
No, sir.
No, okay. In Google Meet we cannot hear the audio. Okay, fine. You can listen. So where they do the tensile test is they do in a machine called universal testing machine. Where they do the tensile test, they carry out this experiment in universal testing machine. This universal testing machine, it has two parts. Okay, these parts can come closer to each other or they can go away from each other. What they're going to do, they're going to take a test specimen. Test specimen means a small piece of metal. They're going to take a small piece of material and they're going to fit it. They're going to fit in the top and bottom. And when they want to conduct tensile test, they will move this far away. The top part, it will go up. So what will happen? The material will get elongated and it will break. When they are breaking, they will calculate the ultimate tensile stress. They will calculate the yield stress values. Everything they will calculate. You watch it. I will explain it clearly.
Conducting tensile test, 500 diameter tensile specimen. Stainless steel material. Engage tensile specimen between crossheads. Apply X-tensometer to determine yield strength of material. After yield strength has been determined, remove X-tensometer and continue test to failure.
Now they are giving a tension force. It is elongating. Can you see the geometry is reducing here? So the geometry is reducing here. Slowly the length is increasing and it got broken. Okay.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm.
So this is the test specimen and you call this as gauge length. Okay. So what they do is after applying tensile force, this will expand, this will extend, this will elongate and it will fail. It will go into the it will go out of the elastic limit and it will break. And after breaking, they will test the length again. They will measure the length again. They will find out before the test what is the length. After the test, what is the length. From that, they will find the elongation. Fine. And you can see this is cylindrical rod, and they can measure the cross section area also. So before the test, what is the cross section area? After the test, what is the cross section area? They can find the change also.
And an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the...
Can you see this? This portion can go up and
Now
down.
he can place
This
the
portion can
threaded
go up and
ends of the
down.
test piece in
And
the
if it
lower
goes
and
up,
upper
there will be
grips of the
tensile
testing
force.
machine.
If it goes down, there will be compressive force on the test specimen. Okay. This is how you fix it. You lock it.
In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters.
Gauge length means what? The length of the test specimen. Okay. So before the conducting the experiment, what is the gauge length? It is showing in the computer.
During the tensile test, the test piece is slowly and constantly elongated with a standardized speed.
Now in the test, what they are going to do? They are going to slowly elongate this. The upper body, the upper that fix will go up. They are going to slowly elongate in a constant speed. That means they are giving a constant force.
Force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation.
Now this rod is being like elongated, and you can see in the machine how much is the elongation. Slowly the elongation is taking
Diagram.
place.
The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Hello?
The tensile test.
Yes, sir.
First test,
Okay. Can you see the code?
Yes, sir.
What about others? Where they went? Only 4 are there.
The timing.
Okay, okay. 5 minutes. Okay.
Okay.
You're hungry?
Yes, sir.
You're feeling hungry?
No, sir.
Okay, this is the test specimen.
Hmm.
Okay. On top they are fixing it. They are fixing it and putting a lock. And bottom also they are fixing it and putting a lock. This bottom is not going to go up and down. Okay. The top portion it is going to go up. If it goes up, what will happen? Goes up, what will happen? On the material, what will happen? This is the specimen, no? So on the specimen, what happens? tensile force will act. Tensile force will act on the specimen. Okay, that means elongation force. So what happens to the this is the gauge length. Okay, from here to here we are measuring the length. This is the initial length, gauge length. L. Now when tensile force is applied, this will be expanding. Now what they are telling is, when a force is given, stress will develop on this material. Stress will develop on this material, and they are telling for some point of time, the stress is directly proportional to the tensile force, or you can tell the stress is directly proportional to the strain. If the stress is directly proportional to strain, then the material is in elastic limit. If the stress is proportional to strain, the material is in elastic limit. Okay. If the stress is directly proportional to strain, the material is in elastic limit. If the stress is not proportional to strain, then the material goes to the plastic limit, the plastic deformation zone. Understood? The material goes to plastic deformation zone. So in the curve, if you look at the curve, it is very easy to understand. If you look at the curve, this is the stress, say Newton per meter square stress value. Okay, and this one is strain dl by L. Okay, so this is strain and this is stress. So what happens when the value of tensile force is increasing, the stress and the strain is like directly proportional. Directly proportional means it will go like a line. Okay, if the stress and the strain, if they are directly proportional, when the tension force is increasing, it will go like a line. At some point of time, what happens? The proportionality is not there. The stress is not proportional to strain. So what happens? The strain will be increasing without increasing stress. Without increasing stress, the strain will be increasing. Okay. So you need to find this point. At which point, without increasing stress, the strain is increasing. That point is called yield point. I'll repeat again. A point on the stress strain curve where the strain is increasing without increasing stress value. Stress means it should go up like this, no? It should go up. Stress means it should go up. Strain means it should go towards right. So strain is increasing without increasing in stress. So this point is called yield point. Fine. After that, after some for some elongation, again the stress will increase and strain will also increase. It will be increasing, and at some point of time the material will break. Material breaks means the stress will become zero. It goes like this. So this point is called breaking point. Okay, the ultimate strength point. Understood? So they compared a normal steel and an high tensile steel. In normal steel, what happens? There is a clear distinction of the yield point. I'll draw that. So what happens here in normal steel? After the yield point, the value of stress will decrease a little bit, then again it will increase. But in high tensile steel and aluminum, there is no such decrease and increase. Okay, it is going like straight. There is a difference they show. So these 2 points, the yield stress value and ultimate stress value. How to find the yield stress? This is the value of yield stress. Okay, sigma. This is the yield stress and this is the ultimate stress. And this is the maximum elongation that is possible in elastic limit. This is the maximum elongation that is possible in elastic limit. When the material is expanding after this, that means it is going into plastic zone. It is going into deformation zone. What is plastic zone? If the material is going into plastic zone, that means it will not come back. It will not come back to the original position. It will be in the deformed state only. Okay. See, elastic limit and plastic limit. I will give some example. You take a plate. You are applying a force. You are applying a tensile force. Let's say 1 meter. It is increasing. The length is increasing to 1.2 meters. That is 20% expansion, and it is in elastic limit. Once the force is taken out, this will again come back to 1 meter. This will again come back to 1 meter. But say it is going to 1.3 meters. 1.3 meters means like it is in a plastic zone. After the yield point, it is going to 1.3 meters. So now what happens? After this force is removed, it will stay in the same 1.3 meters. Understood? So when it will come back to original condition until it expands to 1.2 meters, that is 20% elongation. Till the yield point, it can come back to the original condition. After the yield point, it goes into the deformation stage. And at some point of time, it is going to break. And the value of stress at which the failure is taking place, that is called ultimate tensile stress. Okay, the point up to which the stress and strain are proportional, that is called yield point. This is called stress strain diagram. Stress strain diagram. Tomorrow we'll look at this in detail. Today we'll end the class. Okay. Thank you. Any doubt on this?
No, sir.
Okay.
No, sir.
Thank you.